Alright, welcome to our 7th video in Unit 5, the ideal gas law, my personal favorite law because, well, it just makes things so much wonderfuler. I don't think wonderfuler is a word. Oh well. So, an ideal gas is any gas that follows all the previous gas laws perfectly, even though there's no gas that actually does that. And that's right, we don't really have ideal gases. But again, that means that it has to follow Boyle's and Charles's and Gay-Lussac's. Well, technically in the combined gas law, but that's just combining them. Now, on average, if these all happen all the time. So if we increase our volume, then the pressure is going to decrease. The temperature has to increase. It's all that will happen true, just maybe not as exactly as those laws say. For example, if we double our temperature, we may not literally double our volume. That's basically what we're saying in ideal gas is that every one of these is completely accurate all the time. So, a real gas, therefore, under specific conditions, real gas meaning anything else, like, a gas that we actually use, can actually behave like an ideal gas, at least enough for us to treat it like an ideal gas. Now, this typically will happen most at high temperatures and low pressures. Now, that is quite important, so I'm going to highlight this. Real gases will act like ideal gases at high temperatures and low pressures. Okay? That means that at low temperatures or at high pressures, it doesn't act like an ideal gas. Okay? Now, hopefully your question is, wait, what is high, what is low? There's not quite a set definition for when things are high and when things are low. Given two different temperatures, the one that's higher will be the one that's more ideal. That's what you want to think about. Or given two pressures, the one that's lower will make it more ideal. On average, high temperatures start somewhere around 350 or 400, sometimes even 300, depending on who you're talking about. But keep in mind, not so much room temperature. Like, room temperature starts around, no, I'm sorry. Wow, that was wrong. High tends to start around 400. But, again, all you need to care about is, given two temperatures of 300 and 310 Kelvin, this one will be the most ideal. Or given 1 ATM and 2 ATM, this one will be the most ideal. Because this is higher, it's a higher temperature and a lower pressure. Like, you're good. But yeah, so any other time, it doesn't quite act ideal. Most of the problems, all the problems dealing with what we call the ideal gas law, you can assume they're going to act ideal enough for you. Okay, so assuming they behave like an ideal gas, this is then true. Now, notice this is basically the combined gas law, except we also added in moles. So this relationship has to always happen, where our pressure times our volume divided by our moles times our temperature at one set of conditions will equal the same ratio of pressure to volume to moles to temperature. So if our pressure doubles, our temperature has to double, and all that basically has to stay true, if you will. Now, typically though, we only have gases act like ideal gas under certain conditions. We don't normally have it at two conditions. We're checking it out. So typically, again, we only have this at one condition. We're not saying, oh, we raise our pressure, we raise our volume. We're just saying, hey, a gas at this pressure or volume. Anyway, so that relationship then comes down to R. Now, R has nothing to do with what it's called. R stands for what we call the gas constant. There's not a single R in that entire phrase. I have no idea why it's R. I can't even make a joke about that. It's R. But R, again, represents the ratio of those ideal gas measurements. It is what we call a constant, meaning it is a number that is always the same. That's why it's called a constant, because it's constantly the same number. But that, again, represents this relationship for any ideal gas. Now, commonly, though, we kind of rearrange that, and this is what we call our ideal gas law. or P times V, is equal to N times R times T. Commonly, we call that PIV-NERT. Okay, PIV-NERT. So that is our ideal gas law. It is wonderful, it is useful, but yes, we need to know those values of R. So here are our three most common values of R. 0.08206 times those units, 8.314 times those, or 8.314 times those. Okay, this is the one you need to use. This is one that you will sometimes see if you actually use your textbook, but I really don't care to use it. And this is one that you will use in about 2 units. Feel free to forget it until then. But this way, when you see it then, you're like, oh, hey, I kind of remember that number. And that's about as far as you'll get. Main difference between the top two, up here uses ATM, down here uses kilopascal. Both of these require, as will the ideal gas law, that your volume is always in liters, not milliliters. You're in moles, not grams. You're in Kelvin, not Celsius, and ATM, not anything else. Well, this one uses kilopascal, and if you want to use kilopascal, go ahead. The rest of the world is going to be using ATM. So, there you go. So, the value of R technically depends on the units you're using in your problem, but that's kind of a lie because I'm just going to say always use the first one. If you're given kilopascal, feel free to use the second one, but again, just always go to ATM, it's easier. And as I mentioned, again, we'll commonly use the first one, which again is 0.08206. And thus, we have to make sure we use liters, ATMs, moles, and Kelvin. Otherwise, these units will not cancel out and we will not get whatever else we're solving for. Okay, so let's try this. How many moles of air molecules are contained in a 2-liter flask at 0.07 atm and 25 degrees Celsius? Anytime you see these measurements dealing with a gas and they're not saying something like, oh, we changed the temperature to, or we changed the pressure, or we increased the volume. If they're basically just saying, hey, at some point in time we had this to be true, you're using PIV-NERT. Step 1, write PIV-NERT. Okay. Step 2, I'm going to let you do, but I'm going to tell you, fill in the values they gave you, put a question mark by whatever else they are asking for, and solve for it. It's a lot like that equation Q equals M CS delta T, which I know a lot of you didn't like, but honestly, this is so much easier. There's no delta. You're not dealing with changing. It's just take numbers, plug them in. Again, make sure ATM, liters, moles, 0.08206, and liters, ATMs, moles, Kelvin. Kelvin. With that, take a few minutes, then come on back. All right, welcome back. So our pressure is 0.07 atm, and we can leave that in atm because we want atm. Our volume is 2.0 liters. We can leave that in liters because we want liters. Our N is actually what we're looking for because they said up here how many moles or of air molecules. Couple people probably actually solve for Avogadro, except they're asking for moles of molecules, not molecules. So, a little tricky, kind of. Anyways, so our R, we always know, is 0.08206 liters, ATM, moles, Kelvin. And your temperature is 25 degrees Celsius. We need to convert that to Kelvin. So that's 298 Kelvin. Let me talk about units real quick. I do want units in your final answer. If you start by writing this and you put your units here, but then when you write your calculations you don't have them, I'm fine. If not, I want your units. So, our equation is PV equals nRT, which means that we will have 0.07 times 2.00 equals n times 0.08206 times 298. That is really small, but the answer is already over there. So then our n, basically if we were to mix all those across, 2.00 over 0.08206 times 298. Solving for that, you get you 0.06 moles. Yay, that's our answer. Yay, ideal gas law. Woo. Alright. What's the volume of gas with 900 torr, 4.5 moles, and a temperature? Wow, I did not speak real good grammar on this. And yes, I tried to butcher that sentence. Give you guys a few minutes. Keep in mind, 900 torr, you cannot stay in torr. Have fun. Alright, welcome back. So, Pivnert. Again, they didn't say anything like, oh, we're changing our temperature, we're changing our volume, or whatever. So, that means that you are just using the ideal gas law. That is 900 torr, which, when you convert to ATM, is 1.18 ATM. You've had a video on that. Do not ask me how to convert to ATM. Okay, your volume is, we're looking for, our moles are 4.5. R is always the same. And our temperature is 273 Kelvin. Okay, another way you can do this is you can think Pivnert looks like this. And last time I plugged in the numbers and then moved things around. Another way I've seen people do it is they start by moving letters around. So they get that V is equal to nert over P, and then they plug in numbers. It's the same exact thing. Whichever one looks easier to you, have fun. Either way, volume equals 4.5 times 0.8206 times 273. All over 1.18, which gets you 85.43 liters. And holy cow, that is a huge amount of liters. Except, we have 4.5 moles. At STP, 1 mole is 22 liters. And we're barely a little bit more pressure in STP, which means each, mole will take like 20 liters, maybe a little bit less. So that's actually a pretty good answer. There you go. Ideal gas law. Alright, last example. So, what volume will 12 grams of oxygen gas occupy at 25 degrees Celsius and a pressure of 52.7 kilopascal? Keep in mind, Pivnert needs ATMs, liters, moles, 0.08206, and 2 Kelvin. That's not moles. Get it to moles. That's not ATM. Get it to ATM. Alright, welcome back. As usual, Pivnert. Well, more so right Pivnert. Alright, our pressure is 52.7 kilopascal. We need ATM. So that in ATM is about 0.52 ATM. Alright, we're looking for volume. Our moles are 12.0 grams. Wait a second, that didn't make sense. We need to get these to moles. Okay? You basically end up dividing it by the molar mass of oxygen. Let me actually write that a little differently. So 12.0 grams times 1 mole over 32 grams gets you 0.375 mole. R is always the same. And our temperature is 25 degrees Celsius, which you probably have memorized now is 298 Kelvin. We're looking for volume. So again, Pivnert equals nert. Well, Piv equals nert. That means V equals nert over P. I just find it a little easier to do it without numbers. I feel like you end up writing a bit less. So that gets you really sure what that was. And of course I can't erase it. Why would I be able to erase that? Alright, whatever. 0.375 times something. Oh, and 0.8206 times 298 divided by 0.52. Yeah. Sorry guys, totally forgot to write that. No, I think I actually deleted it. Whatever. Get you. 17.64 liters. There you go. That's ideal gas law. Yay.